To start off this chapter, we're going to take a look at compounds. A good portion, if not all, of this should be a review from the prep class, but let's start. All right, so when we look at compounds, our compounds are formed from our elements. So if I take hydrogen and I take oxygen and I react them together correctly, then I get water, which is a compound. Okay, so in my mixture of hydrogen and oxygen, I can have any ratio I want, but then once we do our reaction, I'm always going to have 2 hydrogen atoms and 1 oxygen atom. Okay, so there's my formula there. To get water, I have 2 hydrogen and 1 oxygen, and I get my 2 waters out of there. Remember that a compound is going to have completely unique properties from the constituent elements. So if I look at hydrogen, I look at oxygen. Hydrogen and oxygen are both gases, and so they have extremely low boiling points. At room temperature, they're already gases. But then if I look at water, the boiling point is 100 degrees Celsius. I have to heat it up quite a bit to get it to go from a liquid to a gas. And so you can see 2 completely different properties. Hydrogen and oxygen, they both either explode or they support combustion, but water is used to extinguish flame. If you go further, like if you look at the SDS for water or dihydrogen monoxide, it's going to mention that it is an inhalation hazard, which because we know we can't inhale water. But hydrogen and oxygen, we inhale both of those, oxygen especially. So completely unique properties. Once I've made a compound, it's its own unique entity. Okay, we've got our 3 major bonding models. The 2 that we're going to focus most on are going to be ionic and covalent. So those are the ones you should be most familiar with. My head covers up this, but if you downloaded the slides, you'll see that this one is metallic. Okay. And so ionic bonding, we know that we are forming just, individual ions and it's electrostatic forces that hold things together, or we have polyatomic ions, still electrostatic forces that hold things together. Covalent bonding, if we think co together, valent, valence, so we're sharing valence electrons, no ions there, right? And then metallic bonding, we're not going to deal with much, but I just want to touch on it again. This is that delocalized electron C model that some metals do, especially pure samples of metals. Okay, so my bond is whatever the force of attraction that holds things together. So I have electrons that get transferred from one species to the other, and then I have electrostatic forces. Those are my ionic bonds. Typically, we're going to look at metals and nonmetals, or metals and polyatomic ions, okay? And usually those polyatomic ions, not always, but a lot of times those polyatomic ions are composed of nonmetals. And then covalent bonds, we're sharing electrons. Generally, these are between nonmetals. What guides really the formation of ionic or covalent bonds has to do with electronegativity. If I have 2 species with very different electronegativity values, one is going to be so much more electronegative that it's going to attract electrons so strongly that it pulls the electrons off the less electronegative species. And we know that metals have lower electronegativity values and nonmetals have higher electronegativity values. And so that's really what's guiding that. With covalent bonds, these are usually between nonmetals. So if I take a highly electronegative species and another highly electronegative species, neither of them are going to be sufficiently more electronegative than the other to force the electrons to completely leave one species. So that's where they start sharing them. Now, there are some nonmetals that have lower electronegativity values, relatively speaking, and some metals that have higher electronegativity values, relatively speaking. So if I get a metal of higher electronegativity value and a nonmetal of lower electronegativity value, there may not be enough of a difference in electronegativity for there to be a complete transfer of electrons. So in some cases, we have observed covalent bond character between a metal and a nonmetal. It's not super common. It does happen. And again, it's going to happen in situations where the difference in electronegativity between the two species is a lower difference. Normally though, our metal is low electronegativity, our non-metal is high electronegativity, and so we're able to get that full transfer for ionic bonds. Okay, and so when we look at our representative particles, we call our ionic bonds formula units and our covalent bonds molecules, because we get discrete individual molecules, whereas with an ionic bond, I have this whole array of positive, negative, positive, negative, positive, negative going through there, and then we represent that essentially with the empirical formula, the lowest ratio of cations to anions. Okay, and so here I have a gas like propane. So if you have like a gas grill or, you know, a little gas backyard fire pit or whatever, or a camping trailer, vehicle, etc., you may have propane tanks around. Whereas a common ionic compound, table salt, sodium chloride. Most everybody has some table salt at their homes. When I form an ionic compound, things happen that allow the electron to be transferred. And so here is another illustration where now I've got two things, completely different properties. Because would you eat sodium metal? No. Would you eat chlorine gas? Absolutely not. That would be toxic. But do you eat sodium chloride? Absolutely. In moderation, hopefully, because too much sodium is bad for you. But point being, or too much sodium ion is bad for you. Point being, though, two completely different starting materials give us a completely unique product. Right? When we do form compounds, we want to be neutral. So with our covalent compounds, this is easy because we're not making any ions. They just share valence electrons. So sometimes they form neutral molecules. Other times we end up forming these polyatomic anions. And so if I have a monatomic ion or a polyatomic ion, it's not stable by itself. It wants to form with something else to be neutral. And so when I have ionic compound formation, I'm going to form in ratios that neutralize those charges. So this should be review. You should have done this like ad nauseum in your prep class, especially when you were learning nomenclature, which we'll review nomenclature in this chapter very briefly, because again, covered it super detail in your previous class. But let's just take a look at this now. Just make sure that we remember how all these ions go together. Okay, so here I have a few examples of some species. These are all monatomic. We're not dealing with the polyatomic ions yet, but take a look at these. Try to remember what ions all these form, and remember, if it's monatomic, we're looking at the periodic table. If it's a transition metal, like this lead that I have down at the bottom, then we need that Roman numeral because we have variable charge. The lead's not, so lead is kind of offset from the transition metals, but it behaves like a transition metal. But the rest of them, take a look at those group numbers. Like calcium is in group 2A, so what kind of ion does it form? It forms a +2. Fluorine's in group 7A. So fluorine, it has a lot of valence electrons. It has 7 of them, but remember we want 8. And so 7 is 1 less than 8, so we make a -1 if we're in group 7A. Remember that the 4 is the dividing line there. If I've got 1, 2, or 3 valence electrons, it's a lot easier to lose those than it is to gain in 5, 6, 7 electrons. And so those are going to form our cations. Okay, once I have like 5, 6, or 7 valence electrons already, it's a lot easier to gain 1, 2, or 3. And so those become our anions. Okay, so pause, take a look at this, see if you can remember what ions all these form, look at a periodic table, and see if you can put together these compounds. Okay, hopefully you paused and tried these on your own, but let's take a look. So calcium makes that +2. Fluorine makes that -1. Okay, and so we want to neutralize this. Okay, so I have calcium at a +2, fluorine at a -1. So I need 2 -1 charges to balance off that +2 charge. So I get CaF2. Okay, silver Okay, now silver is a transition metal, but remember, there's 3 transition metals over toward the right side of the transition metal block that have fixed charges. Silver, cadmium, and zinc. Silver has a fixed charge of +1. Cadmium and zinc each have a fixed charge of +2. So for those 3 species, we don't use the Roman numerals because they're always going to have the same charge. So silver is a plus, and then oxygen, group 6A, so it gets a -2. Okay, so I have a +1 and a -2, so I need 2 +1 charges to balance off my -2 charge. Okay, so I'm going to get that. Okay, potassium and chlorine. So potassium's group 1A, chlorine group 7A. This one's easy, it's a 1-to-1. We get potassium chloride there. Okay, aluminum and sulfur. Okay, so if I think about this, I have a +3 and a -2. What common number is divisible by both 3 and 2? 6. So how many +3 charges do I need to get to 6? I need 2. And how many -2 charges do I need to get to 6? I need 3. So I'm going to get Al2S3. Okay. All right, now my lead. This time we're looking at a lead 4. So I have a +4 there. And selenium is -2. All right, so +4 and -2. Does 2 divide into 4? It does. So I only need one of the +4. And how many of the -2 do I need? I need 2. So I'm going to get P. Let's write the B as we're saying P. PBSE2. So those are my neutral species there. All right. Okay, now our formulas. We represent our compounds with formulas. Now, depending on the type of compound it is, we can sometimes expand that out. So everything will have a molecular formula or a formula unit formula, right? So, you know, by potassium chloride, we just looked at that was KCl. I can write it like that. Now, if I have a covalently bonded compound, then I can expand into these structural formulas, the ball and stick model, the space filling model, because I have discrete molecules. All right, so only things with discrete molecules do we really start representing with some of these other types of formulas, because if we have something that's ionic, it goes together in a crystal lattice, not a discrete molecule. Okay, and so here's some molecules and some different representations. So I've got benzene, which is an aromatic hydrocarbon, acetylene, which is also a hydrocarbon. It's what we call an alkene because it has at least one triple bond. Glucose, ammonia, so all of these are discrete molecules. And so I can represent them in a variety of different ways depending on what type of information I'm trying to get out of what I'm looking at. Okay, when I look at my elements versus my compounds, okay, I have pure substances. I can subclassify that into elements. Elements I can subclassify into atomic or molecular. So most elements exist just as atoms in their natural state. Others exist as molecules. Okay, so what I'm looking at is classification in terms of the particle. And so it's really important when we're trying to visualize and, you know, understand what's happening at the molecular level or the atomic level, because we can't see individual atoms, right? And so we have to have these representations and this understanding of what each one of these things actually is, so that we can start to put a visual of that in our heads. And so we want to have a sense of how these chemical substances look and behave at that molecular, atomic, etc. level. And so the more you get used to these things, the more you start, you know, seeing in this. Like, what's funny, if I see water, okay, if I see H2O written, I've been doing this for so long that, you know, I see a lot of students will draw a Lewis structure, perfectly valid Lewis structure of water that looks like this. okay? But because I know a lot more about water and why water behaves the way it does and how water actually exists in three-dimensional space, I don't ever think of water like this because I know that water is not linear. This Lewis structure, which is a valid Lewis structure, okay? This is perfectly fine. If you're asked to draw a Lewis structure and you draw this, it's fine. However, it doesn't give the whole story because I can draw a Lewis structure that gives a little more information about this. I can draw this because water is bent, and that bent nature is really important to a lot of the properties that water exhibits. And so if you start training your brain to think about these things on this molecular level, you get a much deeper understanding and ability to quickly visualize all that stuff. Okay? All right, and then it's important to understand on the periodic table, most elements are going to exist as just elements, just as atoms. But some elements in nature exist either as a diatomic, so everything that's highlighted in yellow, or as a polyatomic, those things that I have in that pinkish color. So you hopefully are familiar with these from your prep class, at least with the diatomics. I don't know if your prep class, depending on who you had, may or may not have emphasized knowing the three molecular polyatomic ones, but you should have learned at least the diatomics. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. In nature, like if I say, oh, hydrogen reacts with oxygen to give us water, I know that I'm talking about H2 and O2 because those exist elementally as diatomics, okay? If I say, yeah, elemental iodine exists diatomically as I2, all right? Important to know. So these things are things you need to know. And then phosphorus, sulfur, and selenium. When we find these in nature, in their natural elemental form, they exist as polyatomics. So elemental phosphorus is P4. Okay, it's 4 phosphorus atoms hooked together. Elemental sulfur is S8. It's same with elemental selenium is Se8. So you do need to know these. That if I say, elemental phosphorus reacts, boom, you know it's P4. Okay? So I'm going to put this, know these. Okay? You need to know these. There are things that you need to know at recall. I know in looking at the current trends in education, I try to keep abreast of the way they're doing things in K through 12 so that I have a good understanding of what you all, my college students, are coming to me with. And I know in recent times there's been a push to stop some of the memorization, but the thing is in order to do some of the higher level stuff, you actually do need to memorize the lower level stuff. There are things that you need to know like that at recall, like multiplication tables. In order to do higher level math, you actually do need to know those multiplication levels at recall because that's part of basic number sense and the ability to work at a higher level. So this sort of stuff, to have a higher level understanding of chemistry, to have that kind of recall, you do need to know these off the top of your head. Okay? All right, now, my final example for this little section, I'd like you to take a look at these 5 things I have written here. Figure out which ones are elements and which ones are compounds. Okay? If they're elements, identify them if they're molecular. And if they're compounds, identify the type of bond and write the formula from the name, okay? Because again, all of this stuff is stuff that I expect that you studied and learned and were tested on in your previous course, all right? So think about all that. If you're struggling, go back and review a little bit, but pause the video and test yourself on this. Don't just write down what I write down, okay? Because remember, when you're in a testing environment, you can't ask me these questions. You need to know them. When you're outside of my classroom, let's say you get an internship somewhere and they ask you to do something that, the internship requires, hey, you've completed X courses. Okay, well, they're going to expect that you actually have a working knowledge of the material covered in those courses. They might, be willing to help you remember something here and there, but if you go into an internship and, you say you've completed, X number of semesters of chemistry, and you go in there and go, I remember nothing. You're not going to get to keep that internship. You're not going to impress anybody. They're going to expect you to actually know this stuff. So test yourself, see what you remember, pause, and then see if you can answer these questions. Okay, hopefully you paused it and didn't just keep playing the video waiting for me to give you the answer. Okay, sodium chloride. Well, that name right there, I have two different things, so obviously I have a compound, okay? Sodium chloride, sodium's a metal, chlorine's a nonmetal. That IDE ending, yeah, I probably have an ionic compound, okay? So this is compound, it's ionic, and there's its formula. Okay, sulfur. Do I have more than one type of element written there? No, I just have sulfur. So this is an element. Okay, sulfur. Was sulfur one of the polyatomic or diatomics? Yeah, so sulfur is molecular. Okay, and remember sulfur is going to be S8. That's a really bad 8. Sometimes writing on my iPad is a little bit awkward. That's how I do this, is I have two different monitors set up. I have my webcam and I have my iPad, and I have a special program that I run on my computer that mirrors part of my computer screen onto my iPad blown up so that I can write, and then I have the view that gets recorded for you all to see on the other screen. It's taken me a lot of trial and error and figuring out what works smoothest for this online thing. So let's try to write a better 8. S8. Well, that's still kind of funky. It's also weird too, because if I do too much of my hand on my iPad, then it thinks I'm giving it another input. So maybe some more trial and error and figuring out if I need like a glove on my hand or something. I don't know. Okay, water. Okay, water is going to be a compound. Okay, all right. Ionic or covalent? Okay, water is covalent. And we should all know the formula for water. Okay, neon. Neon is just a single element. It is not a molecular element. It is just neon. Okay, and nickel 2 nitrate. Well, I've got a metal and a polyatomic anion, so it's probably an ionic compound. Okay, nickel 2 means it is a +2, nitrate is that. So I'm going to have Ni, NO3, and 2 of them. Okay? If you struggled with that last one, we're going to do a real brief review of nomenclature in our next section. However, if you're really struggling, please, I urge you, go back to some of my other videos on my YouTube channel and look for my nomenclature specific ones and go back and review those, because you've got to know your nomenclature. Not knowing your nomenclature is akin to walking into like a Spanish class, like a Spanish 2 class, and telling your professor that you remember none of the vocabulary from Spanish 1. It's not going to work too well. Okay, you got to know your nomenclature. All right, so that is our look at compounds. So coming up next in our next video, we're going to take a look at nomenclature review. Exciting. Well, I like nomenclature, but I know most students are like, oh my God, nomenclature. So next video, nomenclature.